Okay, so last week we started talking about random process when we have another dimension of the time. And random process was a family of random variables indexed by time. So we add time to random vectors to become random process. That's why it's called process. We also talked last week about basic characteristics of random process. So you did all attendance, yes? I just gonna 1401 is the code. So what else we talked? We talked about characteristic of random process, like mean of random process, m xt. So the mean was average, but like average of all those functions to make another function, function of t. So that was mean. That is expected value of all of these xt's. Let I make this if I can. Like that is easier to write. Everything be okay. Yes. So this was mean. What else? We also know variance. Variance of random process. Variance of xt is like how much this process changing around the mean. So expected value of process xt minus mu. Mu is mean and a square. Similar to random vector, we also have variance for random process. What else we learn? Because a random process is like a signal, sometimes we want to study how this signal changing respect to itself. So how this signal changing in different times. We also have some names for them. Like one of them is autocorrelation. That was R. X, T1, T2, for example, is expected value of X, T1, X, T2. How one signal in different times varying respect to each other. So it's showing how this signal is, acting or working. So this was autocorrelation. And autocorrelation, if we remove the effect of a mean, it becomes autocovariance, or sometimes we just call it covariance. So that was something else that we learned last week. Autocovariance. So was removing effect of mean. So I don't need to write the formula, but it's xt1 minus mu1, mu x1, and xt2, multiply xt2 minus mu x2. So we learned this one. This was like characteristics of random process. So one showing like the mean or average. The other one showing how random process actually fluctuating around the mean. And these two, autocorrelation and autocovariance, is showing how this process is similar to itself in different times. So that's something very interesting that we have it for random process. We haven't had this autocorrelation or autocovariance in random vector, but here we have, because they are changing in time. Sometimes we can study the signal to itself in different times. So that's called auto-covariance or autocorrelation. What else we learned? We also learned about linear state models. Linear state models. So we said linear state models, we defined a state. We said we have, for example, x, k plus 1 is a state that we can write this in a linear form with a matrix A multiply with x, k, like a previous state, plus a noise. This noise called process noise. Do you remember that? Process noise. Why is process noise like, because it's depend on the model. This is the noise, not a measurement noise. It's not a noise that coming from sensors. It's coming from the model. Model has some uncertainty, some issues that we can collect that in this noise. And most of the time, this noise is white noise. Doesn't have correlation. It's a white noise. We're going to talk about white noise more today. So this was also a random process. Why this linear state model is a random process? Because there is a random noise here that makes everything random and make it a process, because in different time it's changing. It depends on the time. But because it's discrete, instead of t, we have k. So the relationship between k and t is that like we have the t is 1 delta t. Oh, sorry, maybe just delta t, not 1. We have delta t, 2 delta t, 3 delta t. This is the sampling times for t. Is coming from that to k delta t. So this k is a discrete form of those numbers, 1, 2, 3 to k, but we have a delta t that is a sampling time to find k, because this is a discrete form. Discrete form, you got sampling in a certain timing, and that timing is a delta t. When delta t going to 0, discrete form becomes continuous. We can see that also today, how we can do that. So anyway, we studied this also. I want just to remind you what we had regarding to random process. Lots of application in random process. And because this is the formula that you can using for motion or tracking, and like robotic movements, is very, very famous in these cases, lots of applications. Okay, another thing that we learned last time was sum of random processes. If two random processes add together, expected value is also add together. If they are independent, if those two are independent, when we are adding them together, they're going to create a new random process that the mean is sum of those random processes, and autocorrelation is also sum of autocorrelation of, because they are independent, everything going to cancel out. So the autocorrelation is also sum of autocorrelation of each individual process. So we learned this stuff last time, very important part. I just wanted to remind you what we had and what we know, but still we are in random process. We have factor of time, but random process, like other actually random phenomenon, can be studied in a discrete form and continuous form. So that's something that we're going to see today. And actually this week, we're also going to have something called Markov process, when you have dependency between these states. So that's very interesting. We're going to see that maybe next time. We're going to start it today, and next time we're going to see that more. So the rest of the class is going to be a little bit about Gaussian process and hypothesis testing. That's it. We don't have anything. I'm not going to teach anything more. That's enough, and it's going to be very useful for you guys. Okay, so let's clean this up. Let's see what we have today. So we're going to talk about a stationary random process, some new characteristics that we have in random process called the stationary. And a stationary random process, what else we're going to see? We're going to see about white noise, Wiener process, random walk as well. I forgot to write it here. We're also going to see how we can model random walk. Random walk is like a drunk person that's walking in any direction. We want to model that. How this is, because this is important. Some type of applications is like that. Like a drunk person that's moving around in any direction randomly. They want to see what's going to go at the end. Where is the destination at the end? So that's also something that we're going to study. That's called random walk. And random walk is a discrete form because you get a step like this, different step randomly, but it has a step, it has k. When you change it to t, it becomes Wiener process or Brownian motion. Do you remember I talked about Brownian motion? When they were watching like Poland that's randomly jumping around. I didn't know why this is jumping around, these particles. And they couldn't find any reason for that. Later on, of course, they found the reason after 70 years. But that become Wiener process. Wiener process is a mathematical method of explaining that motion. Why is important? Because so many phenomena are like that. So many, like the price in a stock market is jumping like that. Or what else? Motion. Sometimes motion, the noise that you have is like noise that coming from sensors, like following this kind of distributions or this kind of things. So that's why we need to study them a lot. Or maybe you just want to estimate a drunk man what's going to end up after 10 steps if you move like that. This is another application too, you know. Yes, so anything that, you know, is previous step plus something random, we're going to study that today. Anything that the previous state plus something random, like you are here and make a random decision. Next time, make another random decision. This random decision with this other random decision, not dependent. They are independent random decisions. But they are random. Sometimes they are Gaussian, sometimes not. We're going to see that today. Okay, so let's see first a stationary. What is a stationary means? A stationary, you know what is a stationary in the meaning. So it means something that is kind of constant most of the time. It doesn't have something varying. So that's true. In statistics or in probability, we call a process a stationary that is not changing over time. It means it's the characteristic or probability or a distribution is not stay the same all the time. The distribution stay the same. The statistical properties stay the same. That's a better way to explain it. Statistical properties. What is the statistical properties? Like mean, variance, you know, more degrees of moments. We have other moments as well. Moment 3, moment 4, we're going to see them. Those are statistical properties. These statistical properties are stay the same or they are dependent on just lag. What is the lag? Lag is that step size between T2 and T1. So, or just depend on this distance between T1 and T2. That's called the stationary. We have different level of stationary. Some stationary are so strict. Some of them are a little looser. But they are good to study them. They are good to know what is a stationary means, because a stationary makes life easy. When you have a process that has some characteristic of a stationary, everything becomes simple. And you can find relationship between actually signal processing and processes there too. We can see that maybe not today, but maybe next time we talk about that as well. Okay, anyway, so that's a stationary. So a stationary means we have statistical properties stay the same, mean is constant, variance is constant, and autocorrelation depends only on time difference. If you have these three characteristics, actually the last characteristic most of the time covers second one as well. Because the variance is variance of xt is equal to expected value of xt minus mu square, and autocorrelation are xt1, because autocorrelation can be studied for t1 and t2, is equal to our expected value of xt1, xt2. How x1, how x changing in different time, or varying in different time, or different by itself in different time. It's a signal that is changing. We want to see what is this difference in different times. So that's autocorrelation, because we want to find the real correlation of the signal with itself in different times. If you have these three characteristics, if the mean is constant, if the variance is constant, constant means it is not the function of t. It's not the function of t. Autocorrelation is kind of function of lag, or a step between T1 and T2, okay? If you have this characteristic, maybe you tell me, oh, this doesn't have all statistical properties. Yes, this kind of stationary is a loose stationary. We have also a strict stationary. So this is example before going to that. So that stationary, as you can see, is a white Gaussian noise. Why white Gaussian noise is a stationary? Because Gaussian actually distribution, all statistical property of Gaussian distribution summarize in just two numbers, mean and covariance or variance. So all characteristics are just these two, and they are constant. So in white noise they are constant, because mu is 0, and variance is sigma squared. So we have that. So this is actually a stationary, but this type of a stationary is a strict stationary. It's very strict, because all of characteristic, all of statistical properties are the same. But like this is not exactly like that. This is actually looser version. So the looser version called white sense stationary. So we have two types of stationary. when these statistical properties staying the same, we just can consider them all of these characteristics staying the same. That is the strict sense. The strict sense is happening for white noise. Or white Gaussian noise, for example. But we also have white sense stationary, WSS. White sense stationary is like what I explained, or that like this. You have cosine or sine plus cosine, or a function of sine and cosine. Most of the time, they create something like that. As you can see, this they are equal when you are shifting in time. When you want to put this in here, you need to shift that, for example, 2 pi or 1 pi to exactly shift it in the same time. So they are autocorrelation depend only on lag, and that lag is like pi, for example, or 2 pi. So that's why this is white sense stationary. Okay, let a little explain. I just wanted to let a little explain about a strict sense stationary. What that means. Okay, so as I explained, first, this is the strongest definition for a stationary. And we are talking about all orders of moments, or all orders of moments. Orders of moments means E of x, x of t, E of x squared, that we can also write it like x t1, x t2. That is the variance. This is mean. This is variance. And this is, we also can make it higher dimension. We call it order. This is first order moment. We call it moments. First order moments is mean. Second order moments is variance. Second order moment. We have also third order moment. It's called skewness. So it's xt1, xt2, xt3. We also have that in random vector. In random vector, you just write xt or x whatever k, or just x, x of x actually, cube. So this is how we do x square, x cube, and then higher dimension. So what that shows, relationship in three different times. This is showing a skewness. This is showing how like checking symmetry, how they are actually like the shape of the points. If you have, like, for example, the points is like that. It has a symmetry part. You know, that's something that we can see. So what else? Yes. So this is showing how asymmetry, like how it's not, you know, how it's distributed, how these points are distributed. Are they symmetric? Are they all, like, for example, they are like that, or they have some skewness? So that skewness even can be computed with the third order moment. That's called moments. But we just study in this class first and second moment. But if we go for rest of the moments, still they are following the same characteristic. If it's a strict sense stationary, a strict sense stationary is very strict. That's why it's called a strict sense stationary. Is a strongest case. We also can explain it like that. This is one type of explaining that. We can say all orders of moments are constant, or in another shape or another way to explain it, we can say that randomness and several time points, that's randomness in several time points, is equal to, when we are write something like equal and a D in top, means is they are statistical behaviors are equal. This showing this is a statistical behavior. A statistical behavior is similar when we are shift that by time. When they are shifted by time, statistical not changing. And it's all statistical behavior. And all statistical behavior means all of those moments. Okay, we don't need to go too deep, but anytime you want to think something like SSS, look at the white noise. Look at the white noise. As you can see in white noise, there is no dependency between each one. And they are all constant. Mean is 0. And variance is sigma square. And sigma square and mean explain everything about that. We don't need any other moments. That's enough information about this. With these two, completely, this signal can be explained. If you just write normal 0 and sigma square, here we have one t as well, or tau, or in discrete form delta t. So this is showing everything about this signal. That is enough. We don't need any other moments. And these two are constant. So this is the SSS, or strict sense stationary. What about wide sense stationary? In this wide sense stationary, we don't need to have all the moments constant. We just need to have 2 first moment constant. Just 2. Mean is constant, variance is constant, and autocorrelation is not constant. It's depend only on lag. So autocorrelation, to make this constant, you need to shift this to this overlap with itself. So it means this is not SSS. This is not a strict sense stationary, but it is wide sense stationary. What is this function coming from? This is a sine and cosine function. In general form, you can write this signal with sum of cosine omega t plus, we can write 2 values, a and b, for example, and these 2 values are bringing that randomness. So we need to bring randomness anyway. And sine of omega t is equal to x of t. So this is the formula to create this signal. This is like sine or cosine signal. You can also write that exactly just with cosine. But inside function of sine and cosine, you need to bring that a statistic form. And here we bring that with this a and b. A and b are consider Gaussian. A and B consider normal distribution or Gaussian between 0 and sigma square, for example. So without this formula is not a random process. It becomes random process when you add some randomness to that, and this randomness coming from this A and B. Okay, we can prove that if we find covariance, if we find, for example, mean, it's going to be 0. If we find covariance, it's going to be constant, not 0, constant, and variance going to be constant, and autocorrelation going to be just function of tau, just function of lag. Let's prove it. So we want to find mean. So we have this function. This is the function A cos of omega t plus B sine of omega t. So, and we want to find mean. So what is mean? I'm going to write it here. Mean of t. Mean of x t is equal to expected value, and expected value can go linearly, x of t, and is equal to expected value of a, because cos of wt, sorry, this is going to be like that, and or omega t, sorry, plus expected value of b sine of wt, and because expected value, because we consider that where I mentioned that, oh, here, because of this, the mean is 0, so the result of this is 0. So this is constant. What about autocorrelation? Autocorrelation is also can be computed. Autocorrelation is for T1 and T2 is equal to expected value of xt1, xt2, okay? And we just need to use this. We just need to substitute this inside, and we're gonna get expected value of a cos of omega t1 plus b sine of omega t1. Oh, and product of this with a cos of wt2 plus b sine of wt2. We can bring expected value inside linearly. So when we do that after multiplication and make that simple, because expected value of A is 0, and B is 0 as well, the only thing that remains is going to be, after canceling them out, is going to be something like expected value of A square cos of W1 cos of W2 plus expected value of B2, B2, yes, cos of W1, this is sine, sorry, sine of W1, sine of W1, sine of W2, and this is, we know that this is sigma square. This is sigma square. This is also sigma square. It's given here. And the rest is we can factorize sigma square out, and the rest is familiar. No, if you know in I don't know which, maybe linear algebra, you know that are you gonna write the formula for that is saying cos of A minus B is equal to cos of A cos of B plus sine of A sine of B. So we have this one. The result of this gonna be sigma square cos of, we have a W here, W T1 minus T2, and that's T1 minus T2 is lag. That's it. So as you can see, we proved that autocorrelation is function of lag. It's not depend on T1 or T2. It depends on the difference between T1 and T2, that's called lag. So this is the third characteristic. But if you prove these two, easily you can prove that also variance is constant as well. Okay, because we can write variance also the same. So the variance of xt is equal to autocorrelation in the same time. So in the same time minus, because we need to remove the effect of mean, m square xt. So this is constant, and this part, this is constant 0, and this part, because it's just Rx of 0. So that's also constant as well. So when you get these two, I mean the mean is constant and the auto correlation, it depends on lag. You also can prove that the variance is also constant as well. So we proved that this A cos of omega t plus B sine of omega t is a wide sense stationary, but is not a strict sense stationary. Why is not a strict? Because this is depend on tau, depend on lag. Still depend on something, is not constant. Okay, so that's the point. Any question about this? Did you get the main idea? What is a stationary means? What is a strict sense stationary? What is wide sense stationary? Wide sense stationary is like a loose version of that. Just you need to have two moments as constant. And autocorrelation is also the function of lag. That is, lag is a difference between x, like T1 minus T2 or T2 minus T1. Okay, so yeah, that's good point. The relationship, if you have a strict sense stationary, you always have wide sense stationary as well. But not all wide stationary are strict. That's always makes sense, of course. Let's do one eye clicker. Okay, so I gave you two functions, two actually random processes. Why they are random process? Because we have WT there. And I'm asking, let I active this eye clicker first, and then read it. And I'm asking which process is stationary. So you think about it, I'm gonna active that now. I need to log in. Okay. Okay, so start the class and start this. Okay, good. Okay, now the class is started. So let's see. I gave you two random processes. One of them is 20 plus WT, and the other one is 20 plus 0.5T plus WT. I'm asking, and they're both like modeling for temperature. We are modeling temperature with these two random processes. It means the temperature is in time t is always something around 20. 20 is a mean, and we are jumping around 20. How we are jumping with that random process? This WT, that is white noise. This is white noise. We need to have some information about this white noise for sure. If we consider this white noise, because this is white noise, oh, still I didn't talk about white noise. Okay, white noise doesn't have correlation. We just need to, we know just about whitening from before, that whitening means we are removing correlation. So autocorrelation is 0 in this case. So the shape is symmetric. Okay, so we have a noise that is white noise. We don't know if it goes Gaussian or not. We just know this is white noise. This is the case A. In case B, the new temperature is 20 plus a function of t plus that randomness. So it means temperature is slowly increasing, very slowly increasing. So I'm asking which one is stationary? Which one? Case A or B? Let's see what you respond. Yeah, mostly you got one, and that's actually correct. The one is because it's not function of t, is that omega t or the WT is actually white noise. Is white noise and is actually correlation is 0. So this is stationary. But let's ask you, yeah, that's correct. That's good. But I'm going to add something else to that question. Let's close this. I want you, with your partners, talk about which kind of a stationary is that. Is that a strict sense or is wide sense? Okay. So we want to see, so this is the answer. This is a stationary, but we don't know which kind of a stationary is that. If we want to see which kind of a stationary, which is that, which part of this is more important for us? Which part is important? Which part of that is showing what type of stationary is that? 20 plus WT. 20 plus WT. What about we find some characteristic of that? For example, can we find mean? Yeah. What is mean in this? Mean of, in case A, mean of x is equal to what? When we are get, mean, when we average them out, that sigma is the W has this characteristic. The mean of WT is 0. So when we get mean of this, the output is 20 because mean of WT is always 0 because it's white noise. White noise is also, mean of white noise is also 0. I should mention that as well. So in this case, mean is constant. What about autocorrelation? Let's find autocorrelation. Autocorrelation depends on something. I should explain white noise first and then explain this. Anyway, autocorrelation in white noise is equal to autocorrelation of white noise is sigma square delta Dirac function. We're going to see that in next slide. So this is also something that the function of tau. So this is the function of tau, not constant. So with this information that I mentioned, mu is 0, and autocorrelation, because autocorrelation of the first one is equal to autocorrelation of W, and autocorrelation of W is equal to sigma square Dirac delta. Do you remember Dirac delta? Dirac delta function? Dirac delta function was very important when you want to get samples from a function. It has some beautiful characteristic for that, for sampling. That is the main point of that. So anyway, we're going to see more about Dirac delta, but the autocorrelation for white noise is this formula. So what that means, it means if t is not equal to 0, if tau is not equal to 0, Dirac delta t is 0. So it makes everywhere 0. That's why we said autocorrelation for white noise is 0, but anywhere not in tau. When tau is 0, the autocorrelation is actually sigma square. This is characteristic of this function, this Dirac delta function, because Dirac delta function, when you get integral, the area under that is equal to 1. That's the characteristic of the Dirac delta. Do you remember we said about Dirac delta? Dirac delta is like this function. It's everywhere 0. Just in 0 is infinity. Just in 0 is infinity. This is, imagine this is tau. We show it with an arrow, something like that. And this is Dirac delta function. And yeah, this Dirac delta is very important, specifically for sampling, as I mentioned, because when you actually multiply that by a function and get integral, you can find exact point of that function. You know, for digitization, it's very important. That was the characteristic of sampling characteristic. It's actually, I'm going to write it just to remind you how amazing was that. If you get integral from minus infinity to infinity from xt, a function that is continuous, and multiply that by this Dirac delta in t minus t0 delta t, this integral gonna be equal to x t0. So this is called sampling. We do sampling using this Dirac delta function. And it's like mathematical imagination does not exist. We can have something to go to infinity, but we just can explain that. This is actually the time that they were working in quantum physics, and they wanted to see how they can study particles in one specific, they want to study just one specific particles. At the same time, they were, you know, in a continuous form, and you wanted to study just one particle, and they created this direct delta function to just mathematically explain it. But this, in reality, does not exist. Anyway, it's good to know that for your in your career, because you're gonna see that in so many things related to the signal processing. And for modeling, of course, modeling any random processes, you might know how to digitize something. Yeah, in electrical engineering, we have so many. And digitization is very important. Sometimes you need to digitize something that is very strange. Like, for example, in my job, I need to digitize level of trust. Imagine trust between agents. You want to model it. And that's a random process, actually, because the trust is moving in time. Trust is changing in time. It's a random process, the trust. But how you can explain trust? What is trust means? Is there like reliability? No. Reliability is, maybe we can define reliability as trust to yourself, reliability. But reliability, but trust is between multiple, actually, agents. We call them agents. So they need to trust each other. It's like a relationship in higher dimension of relationship. So you want to see how you trust your friends and how you can digitize that. Digitize that means how you can model that in a way that you can represent that with the function, with the you know, numbers, with some numbers, and it's very complex things. And the main thing about the trust is that it is not Gaussian. Trust is not changing smoothly. Suddenly you're jumping in trust. For example, trust starts, making trust is very you know, slow, but losing trust is very, you know, sharp. Like you trust your, for example, friend, and suddenly you see something and you just break up. you just make your trust down dramatically. So that's a very interesting part, and that's a future for, because I don't know if I told you guys, the future gonna be when multiple things helping each other to do the stuff. We not, this centralization is finished. We want to decentralize things. We want to make everything to help each other to make a decision, because it's better, is a better decision, and is also you can expand it. You can make the problem bigger because it's distributed decision making. Is every agent or every part of decision is very small, but together they make something huge, and they have lots of power if they get together. So the kind of model is decentralization, and in decentralization, actually, we might know about this stuff. Anyway, I jumped around so much. So let's go back to this example. So A is the correct answer. Stationary. Which kind of stationary? Wide stationary. So that's the point that we need to know. WSS. So this is W wide sense stationary. Okay, let's go another thing that we need to know. We already talked about whitening before when you are removing correlation, but we also have white noise. I think we a couple of times maybe called that, but we didn't explain it completely. In this slide, I'm going to explain that completely. What is white process? Sometimes called white noise as well. White process. White process is a type of process that there is no correlation over time. There is no dependency over time. You can't find piece of this that overlap it exactly the same, something like that. You can't find that. This is white process. White process, no correlation over time. Each sample is independent of others. As you can see, it's too random. Even two close one, they are, independent. But if we get too close, like we go 0, in that case, they are a little dependent. Autocorrelation, even though we don't have autocorrelation, in tau is equal to 0, we have autocorrelation. We have some value in a continuous form. And this value is sigma square direct delta. And I already explained this. This direct delta is 0 everywhere, just in tau, when we get integral, becomes 1. So our x of 0 is actually sigma squared. That sigma square actually kind of specifying how much this is changing. This sigma square defining how much this is jumping around. Like in this example is 1, because it's changing between 0 and -1 and 1. And the mean is always 0. Okay, so this is white process. So no correlation. The only correlation is the autocorrelation coming in when lag is 0. Is 0 in other places, in the same place, in the same time, when T1 and T2 are equal, and lag is 0, we have this autocorrelation. So this is definition of white process. Why white process is, another characteristic of white process before I go into that, is that there is no memory of past. We don't have any, we don't keep anything about past. Past do not affect future. In this case, but in our case, of course. And in Markov process that we're going to study soon, we're going to see the future is depend on past, but not too far past, just one step past. If you go too much past, if you can model a system that makes decisions based off all the past, that is very advanced model. With actually, because that's the evolution actually happening. We want to say what is the next is depend on the previous state, two previous states, and go million steps before. And this is how we can model evolving something. It depends how much information you have. And these informations are all differentiation, isn't it? When you get one differentiation, you go one time, 2 times differentiation, go more. And this is how we can model all the evolution or evolving something with just mathematical way, with differential equation. We might see that, you might see that in other classes, of course. Okay. I just want to, just one example about this differential equation, like about if you go one differential equation from position, you go to velocity. If you go 2 differential equation, you're going to go from velocity to acceleration. If you go 3, you're going to go jerk, for example. If you go more, you're going to get more information. It depends how much you want to go more precise, how much you want to be more precise. Most of the time, position and velocity is enough to predict future, but if you go with acceleration, your estimation or your prediction is better. If you go for jerk, it's going to be much better, and then so forth. If you go for 4 degree of pass, you can get better prediction. That's what I wanted to mention. Okay. So no memory, past value do not affect future, and completely random behavior over time. Examples. Example of white noise is the noise coming from sensors, or thermal noise in electronics. In electronics, you have thermal noise happening a lot, and that's white noise. Also, sensor noise in ideal case is considered white noise. Most of the time, we consider most of the noise white noise. However, when we are saying white, we are not talking about distribution. It's not always normal. You can make it normal as well. It can be Gaussian white noise in that case. But if this is white, not necessarily is Gaussian. Okay, we can add Gaussian to that as well. Okay, so that's something we let's go for a random one.